So okay, so we are going to start with our topics now, which is the, let me title the topic. Okay, it's the orbit equation for one body problem. Now, what we'll do is we'll consider the body of mass mu. We'll consider a body of mass mu orbiting around a central point under the influence of a radially attractive force. So, under the radially attractive force. So, what do you mean by radially attractive force? So, a radially attractive force, as I said, is nothing but the gravitational force minus G m1 m2 upon r square. Now, you need to know that the minus sign here denotes the attractive nature of force. And as I said in the last lecture, how to read this, it's read as the force on body 2 due to 1. And here is an r square. Remember that it's inverse square law. Now, we have claimed in our lecture that the force is conservative. In the earlier lectures that we had in our classroom, I have shown you how what it takes for the force to be conservative. I briefly gave you the steps to find if the force is conservative or not. One of the way is to check the vanishing of the curl. If it's equal to 0, it's a conservative. If it's not equal to 0, it's not conservative. So we saw, and I gave you a very brief steps from the work. From the definition of work. Now, whenever the force is conservative, I can define potential. I can define a quantity called potential energy. Just think it off in this way. So now what I will do is I'll set the potential at infinity to be 0. Alright? Because I have that freedom to set the potential at infinity to be 0. Now I have to check, is this reason my physical question? Physical reasoning is required. Now actually, yes, if you see the potential, it goes like 1 over r, and as potential reaches infinity, as the distance reaches infinity, our potential tends towards 0, which is viable from this particular equation. So my claim is correct. So now let's go. So I wrote what I know. I know the force. I wrote down an equation for that. Secondly, I know energy, right? Energy is half mu square, which is kinetic term, plus potential energy, and potential energy, as I just said, is derived from the force, and which is negative term on r. Now, I want to emphasize that v here is the relative velocity. It's a relative velocity. Alright? Now I said that we need to use the plane polar coordinates. So, how to bring that plane polar coordinates into picture is the velocity. We will write velocity in plane polar coordinates. So it has two components, the radial component and the theta component. So, and it is easy to see that the radial component is r dot, the velocity of the radial component is r dot, and the theta component of velocity is r theta dot in plane polar coordinates. Now I will say the magnitude of this vector, which is simply represented by V, is writing in a differential form. Nothing interesting, just writing what I know. Now V square, I have V square over here, so I need to write the V square equation. In order to write the V square equation, r cap square plus r theta dot theta cap square. Now the combined terms, which as we use in a square plus b square plus 2ab equation, this combined term is, let me show you, this 2ab, which is a combined term, will be absent, to speak, will be absent. Why? It's simple. I mean, when we take the scalar product, the unit vector r cap dot r cap will give us 1. Similarly, the scalar product of two same unit vector will result in 1, which is theta cap dot theta cap will result in 1. But the scalar product of two different unit vector will result into 0, which is 0. Theta cap or r cap is equal to 0. This is the reason why we don't have this combined equation over here. Alright, so our velocity square is, so this r cap square is nothing but r cap dot r cap, which is 1. So I can simply write it as r theta dot square. This is my velocity. I'm going to substitute this velocity over here in this energy equation. So I'll get an equation. It's very simple. If you see, I haven't used any mathematics so far. It's just the substitution and the physical reasoning of using the plane polar coordinates. Alright. R. Alright. I have an equation. This is my energy equation. Now, as I told you that we need to find an equation of motion in terms of constants of motion. So what are the two constants of motion that we know? The two constants of motions are energy and angular momentum in case of central force motion. Angular momentum. So we have an equation for energy. I'll try to find an equation for angular momentum. You see, angular momentum is a vector quantity. It's a vector. So vector quantity needs to be defined with respect to something. For our case, let that something be the origin O. Alright? For our case, let that something be O. So I'll define L vector. Let's say just L vector, not for this case. This O here represents with respect to origin. Alright, just remember this. So how do we write angular momentum? So a basic definition is the magnitude of L, the magnitude of angular momentum is mvr, right? That's the basic definition of angular momentum. So in vector it is defined as r vector cross mv vector. So for our case, we don't have m, we have mu as our mass. So r vector cross mu v vector. Let's expand this. Okay. So r vector into writing the same equation. V vector. So we need to write v vector as in plane polar coordinates, as we saw, and I'm also going to write this in the component form, alright, in component form basically. So this is r cap. Just consider it for now. It doesn't need to be defined with the origin. It's understood because it's one body. Mu v r cap, okay, r cap plus v theta cap. Now, so basically again we are going to use the vector analysis. In cross product the picture is quite different. The cross product of two same unit vector results in 0, but the cross product of two different unit vector is not 0, but rather it's some other combination of this, which is another unit vector. So it's basically, it's kind of a rule: r cap, theta cap and k cap. This picture actually helps us to denote the signs of these components and so on, so it will keep the track of signs. So r cap cross theta cap will result into a new vector, which is k cap, which is positive because it is in the direction of the arrow. But if it's not in the lecture, not in the literature that we are going to study, but I'm just telling you, if we have a situation like this, the arrows, it will result in k cap, of course, but the arrows are in the opposite direction, so we need to put a negative sign, a minus sign. So for now we are not going to use this because our component is in the form of r cap cross theta cap, which is k cap. So I write my angular momentum equation as, so this equation vanishes because this r cap, and here's an r cap, the r cap cross r cap will result into 0. So this my first equation just vanishes. So I have mu r theta k cap, and I know my theta component of velocity is r theta dot. So mu r square theta dot k cap. So what I do is I define this as my L vector. So k cap. That's a simple equation. So I define my L vector to be mu r square theta dot. Not a vector, but basically just L, because it's in the vector now. It's just a component. So if you see, I can devise theta dot from this equation. Theta dot is nothing but d theta by dt, which is L. So mu r square, denominator, d square, mu r square. But if you see, I can substitute this theta dot over here in the energy equation, right? Let me do that. So I can rewrite my mechanical energy in this form, which basically gives me energy of mu r dot square plus half L square upon mu r square minus G m1 m2 upon r square. This is our energy equation. We have two constants of motion, energy and L. So we wrote the one constant of motion, which is energy, in terms of other constant of motion, which is L. It's beautiful. Now what can I do is I can devise r dot from this equation. See, I told you, if I want theta dot, I want r dot. If I want r, I need theta, because they are interdependent, because our goal is to find r as a function of theta, right? So I can get r dot from this equation in the form of two constants of motion, which is energy and angular momentum. So let's find r dot. So r dot is dr by dt, which will okay, so my entire equation will have energy is positive because it's in right hand side. This will go there, it's going to be negative, and it already has a negative sign. Go there, picks a negative sign, it becomes positive. So it's minus. I'm sorry. Let me rewrite it. Okay. I'm sorry. Okay. By dt r dot, right? So it's going to on scale, and this negative becomes positive, and we have r, and it's going to be, and since we have a square over here, and the 2 is in the have 2 and moves numerator goes the denominator, and yeah, the half and half square root, the square root because we had r square. So as I told you, we need, our goal is to find r as a function of theta. So with these two equations, that's theta dot and r dot, can I find r as a function of theta? Absolutely you can. See, it's very easy. It's just the manipulation of the differential equation. So I can write d theta by dr as d theta by dt, d theta by dr, which again goes as d theta by dt upon dr by dt. I know d theta by dt, I know dr by dt. It's here and here. It's over here. So it's easy to write the differential equation. D theta by dr is equal to L upon under root 2 mu. You can see it's not that difficult. Upon E minus L square, the same term, just the 2 go outside. It's just 2 mu r square, I mean the 2 over here, not the 2 over here, and m2 on r, and so this is our equation. So let me write it neatly. I will take this dr with this the right hand side. L upon under root 2 mu 1 upon r square, and we have this term which is E minus L square upon 2 mu r square plus g m1 m2 upon r and dr. So we got our equation, we got our differential equation. So our goal now is to simplify this equation, to simplify this differential equation into something viable, or say accessible to our own perspective. So that's what we are going to do. There exist two methods. So we have two methods. So we have two methods, method 1 and method 2. Method 1 follows the original Newton's equation, I mean Newton's approach, and second is slightly manipulative approach, which is quite good actually. So it doesn't matter, so it's up to you which equation, which method to use. So I will just upload both the methods so that you can get a clear head and how the equations work. So in next video I'm going to upload my first method, and after that I'm going to upload my second method. It hardly takes 20 minutes for each method. It takes about 10 minutes for you to solve, it takes 20 minutes to explain, so don't be afraid of timing, just do it.